Let's go. So we left off talking about Arrhenius versus Bronsted theory of acid and bases. Okay. We looked at Arrhenius versus Bronsted theory of acid and bases. So we said, and again, in regions, are they going to hold the fire to their feet by messing up acids between Arrhenius and Bronsted? The answer is probably not likely, right? So you should be able to rewrite this chart from memory. Wink, wink. All right. You should be able to do this from your memory. All right. It's not in the reference table, right? You should know this. All right. So Arrhenius is regarding ions, and Bronsted is that. Now, like I said, in the regions, they're not going to make a huge distinction if you get these two confused. If you're going to upper level science classes, you are expected to know the differences. That being said, right, it is the same concept. Conceptually, it is H plus that is being donated in terms of an acid. So acid is pretty easy. Anything that is going to donate or give off an H plus is an acid. Anything that gives up, and then when it gets to bases, that's where you have a little bit more difference, right? Arrhenius, they're both donators. Acid and bases are both donators in Arrhenius. It's just that they donate two different ions. All right, Arrhenius, they're both donors. They just donate two different types of ions. Arrhenius, they're both donors. They happen to donate two different types of ions. Bronsted-Lowry, acid is a donor, base is an acceptor. They donate and accept the same thing, which is a proton. And we established that proton is an H plus. All right, we established that proton is an H plus. All right, so how does this fix ammonia? Ammonia was a problem before because it doesn't fit the Arrhenius base definition. The Arrhenius base definition of tells us that it's supposed to be a hydroxide donor, and ammonia does not have OH visible. That's why Bronsted-Lowry, and ammonia is not the only one, by the way. There are other substances. Ammonia happens to be the one example that is so common that the regions decide to put it on there, okay? All right, so that being said, knock on wood, but 99.62% of the time, if they ask you the exception to the Arrhenius definition, it'll probably be ammonia. They'll try to stick to what's on the reference table, right? So how does this fix this, right? It fixes this because we know that as ammonia becomes ammonium, right? This is ammonium. How do you know that? Because this is from where? What table? Table, is it J? Ammonium. Table what? Yo, you should know that, man. Table what? What does that look like? So what? This is what? What do you call this? A what? Polyatomic ion. So that makes it a table. Right. So table E is where we get that from. Okay. So ammonia can turn into ammonium. Right. And I know the video of the lessons, if you've been watching them, are going to overlap. I do that purposely between the two videos so that there's about approximately 30 minutes to 40 minutes of an overlap between the two lessons, right? So then if you do contiguously watch it, because I always record the double periods, so if you do that, you'll get double reinforcement, right? However, if you look at this, then what do we know? This is what's going to happen. So we know that because NH3 accepted an H plus, this makes it a Bronsted base. Everybody understand, right? This makes it a Bronsted base. All right, this makes it a Bronsted base. So that's why this fills the idea that it is a base, okay? Boy, am I glad it's Friday, because my arm is about done. All right, so here it is. All right, so however, anyone else notice something interesting? What else do we notice that's interesting? Arrhenius was never wrong in the first place, right? Arrhenius was never wrong. What do I mean by that? Arrhenius says the base is something that produces or donates OH minus ions, right? But what do we notice here? We notice here ammonia reacting with water. Anybody know from biology what the pH of water is? Yes, sir. Zero. Not zero, right? I mean, I know where the idea. Anyone know what neutral pH is from bio? Dude, this is from bio. Yes, sir. Nope. Yes, sir. Nope, it's 7. 7 is neutral pH, right? You should know that from bio, guys. Again, right? You guys are scaring me. You're supposed to remember stuff from previous years, right? Like including elementary school math, English, right? And so forth, right? All right, so don't do that. Moving forward, you should try to remember everything, yeah? It'll help you. All right, so moving on, right? And I'm not being sarcastic. I know it sounds like sarcasm, but it's not. I'm being serious, right? Guys, seriously, right? Don't go through life where when you learn a new bit of information, you're like, oh, okay. And then you just move on, right? Life isn't about a quiz at a time, right? It's about the whole thing, right? How you end your race, right? All right, so moving on. So what do we know? We have neutral water, neither acidic or basic. We have ammonia, but what happens? Ammonia will turn into ammonium by ripping a H plus off of the water. Hey, what do we end up having in the end? The water turned into a what? Right. And if you think about it, is this an Arrhenius base? And the answer is yes. Not directly, but indirectly, it actually did donate, right? Imagine if donating money makes you a base. The difference is this. Sierra has a big bag of money and you walk around with it and people see your money. They're like, oh, there's someone with money. So therefore, we know she's going to be a money donator. Yes. And therefore, you're a base. Everybody understand that? That's what NaOH, KOH, right? MgOH2. That's what that is. That's why it's obvious. You see the money bag or the proton bag, you're like, that's a base. Not the proton bag, hydroxide bag, right? Right? But then when you look at ammonia, what's ammonia like? Ammonia is like Dennis, where you don't see him with money. And you think he's not going to be able to donate money, which is not going to make him a base. Except what does he do? He will go up to Tiernan, who has money. He'll beat him up, rip his money off, and then he'll throw it out. Did he donate money today? Yes. Through who? Not directly, by through Tiernan, who's the poor water molecule. Do you understand how this works? So in the end, Arrhenius isn't wrong. It's just that he wasn't looking at it in the right way. Arrhenius said bases are something that donates OH minus directly. That's where he was wrong. So in the end, Bronsted-Lowry definition is much more modern and more accurate because here's how it works. Anybody that can cause, right, extra amount of H plus to float around, don't care how it did it, if it can do it, is an acid. Anybody who causes H plus to be absorbed out of the water, don't care how you do it, is a base. Everyone okay? And that's it. Now, like I said, there is a third guy called Lewis definition. We are not covering it in regions, right? But anybody remember Lewis from previous year units? What was Lewis famous for? Lewis what? Dot diagrams. Anybody remember what those dots and dashes represent? Yes. Right. Specifically, valence electrons, right? So what do you think Lewis definition is based on? Valence electrons. So it's not a hard definition to understand, right? So I'm just going to tell you, even though you don't need to know it. So, and I'm not even going to write it, right? You're welcome to write it, but just make sure if you do, say that it's not, you're not responsible. Lewis defines now acid as an electron acceptor and a base as an electron donor. And interestingly, that is the most correct definition of acid and base, right? So anybody that's able to, grab electrons out of a solution is considered an acid. Anybody that can actually give electron into a solution or into somebody is called a base, right? And then if you think about it, the real crying shame here is that with electrons moving on and off of substances, and the fact that we just finished what unit? Electrochemistry and redox, right? That's how the two units are connected, which is, I personally think it's cool as heck. But the problem with this is that a lot of teachers are complaining that they don't really know how to explain it well, and the kids are confused. So New York State Regents dropped it. They got rid of it, right? So if you are really interested, and if you like this stuff, then you can try to look more into it and read about it, right? Like, for example, nobody's stopping you from, like, over the summer, like, Googling Lewis acids and reading up about it. And it's like, how does that actually work, right? Right. And what, yeah.
So I asked,
Speak up, sir.
I asked this question yesterday. You told me to ask it again.
I did. This is why I asked you to ask it again, because I don't even remember you asking questions. Go ahead.
Because ammonium has H4, does that make it a polyprotic?
Oh, that's a great question, right? And I'm glad that I asked you to ask. And I was in the back of my mind, and I was like, wait, isn't this the class where I explained it? I was going to explain to the next period class, right? But it's this class. All right, so that's an excellent question. Let's think about that for a second. Let me make sure there isn't anything up. Yeah, awesome. This is empty space, right? So our friend Abel asks, since ammonia has NH3, how many protons do you see? Raise your hand. NH3. How many H's do you see? It's not a trick question. Yes, Jane. 3. So Abel's question is, well, then could it be a multiple polyprotic, right? Because remember, what's an example of polyprotic? H2SO4. What's another one? H3PO4, right? No. Doing class right now. Come back, right? I don't care. No, dude, I'm recording. I'm having class. Not right now, okay? You know better. All right. Moving on. All right. So, what was I saying? I'm sorry about the interruption. Polyprotic, right? H3PO4, H2SO4, right? I'm sorry, H3PO3, right? Or PO4, right? But anyway, this is why do not interrupt my class when I'm having lessons, because my brain, right? I'm a scatterbrain. I'll admit it. And what happens? I go off topic. I literally wasted another 10 seconds telling you that you shouldn't interrupt my class, right? Right? And you're thinking, oh, it's okay. Mr. Kim loved me when I was in his Regents last year. Sorry, guys, that's last year. Next year, guess what? I'm going to like my Regents kids better than you guys. I'm sorry, but that's what it is, right? That's my job, right? That doesn't mean I don't love you guys as students. Just stop interrupting me, right? See, look what happened. That's 15 seconds we lost. All right, let's keep going, all right? I mean, you can say hi, but definitely not like, hey, can I return my textbook right now? No, you can't return your textbook, right? And you're thinking, well, Mr. Kim, what's a big deal? It's just, no, because you know me. You know what I'm going to do? I have to pause, open up my Google form where I have the book number and go through all that. Oh, which reminds me, I got to do that with you guys too, right? So I'm just going to throw it out there right now. I mean, it's way far out. For the New York State Regents, I will be collecting the textbook back, not the review book, not the flap. That's yours to keep. The hardcover textbook that I gave you in this class, I will be taking those back. I would like to collect it before the last actual class with me, but for some students who want to use it as a reference to read and study into the Regents, right? I'll let you hold on to it and you can return it to me hopefully during the Regents, okay? All right, so moving on. All right, so let's go back to Abel's Excellent question. So the question is, can NH3 give off more than one proton? All right, so to figure that out, we use what's known as God-given common sense, right? Are unicorns real? No, why not? If it were real, you would have seen it. You understand? Right? So let's see. Let's consider for a moment if ammonia could grab, polyprotic means what? More than one proton gained or lost, right? So let's assume that it is, maybe what we're going to do is a what if NH3 grabs not one, but two protons. You know it can grab one. That's okay, right? So you know this is definitely a possibility. But, right, do we know, also if you're late, walking in silently, right? Hey, if you're going to be late, I'll address it later, right? Okay. All right. So moving on. All right. So here we go. So we have that, right? And then now what's next? All right. Let's take a look. If it is true that this is the case, right? Then let's take a look. You got NH3, right? Grabbing not one, but two protons, right? And you're thinking, well, wouldn't it grab two protons out of single water? It can't, because then you would have what? Two H pluses and one O2 minus. Doesn't do it that way. It'll actually grab a proton from each water like this, okay? So you don't have to know that, but you know, it makes sense. All right, so now if you do that, what happens? Then you would end up with two water molecules that have lost proton each. Would you agree? But what happens over here? You would end up with NH what? 5, and then what would be the charge? Think about it and raise your hand. Yes, sir.
+2.
Right. It's +2 or 2 plus. Same thing, right? Now, raise your hand if you've seen NH5 2 plus in your life. Exactly, right? So it's like the unicorn. If you've never seen it, probably doesn't exist. So therefore, what happens? Abel is going to be like, he's going to think about it. He's going to say, nah. Right? Dang it. So it doesn't happen. So it's not a polyprotic base. But then the question remains, but it's got all those protons. Could it rip off extra protons? Let's look at, so ready? So we know that it's not a polyprotic base. We know that because it makes no sense. NH52 plus, never seen that before. So let's look at the other way. What if it's NH3, right? And it turns it into an acid. That would mean that it would give what? Give a proton or take a proton if it's a Bronsted acid? Give. If NH3 gives a proton, what would it be? NH what? NH2. And will it be neutral or will it have a charge? Yeah. Yeah, what would it be? It gave off an H plus. So it would be -1. Good. All right. And then you'd end up with H3O plus like that. And once again, the question is, when was the last time you saw or heard of NH2 minus? Anyone? Nope. It's also a Na. So therefore, this is not possible. So therefore, also not a polyprotic acid. Although, remember when I told you a lot of stuff that I tell you in class, I lie through my teeth, right? This is correct for general chemistry. When you get to biology, you will see that NH2 minus does exist, except they don't float around like that. They're attached to side of organic molecules. It's called the amine group. And if you were honors bio who came into our class, right, Doc probably covered it, right? And then if you're AP bio, you should cover it. But according to AP kids that I have in my chem class who took AP bio last year, they claim they don't know it, which I think they're lying, right? So what does that mean? The conclusion is NH3, is it polyprotic, yes or no? No, it is not. So the conclusion is that NH3 is a monoprotic acid or base? Base. Okay, only. All right. That's an excellent question. Actually, I meant to talk about that, but that's great. Everybody okay with that? Now, here's a point. If somebody asks a question and Mr. King goes, that's a great question, and I explain it, and let's say if you're sitting in the audience right now saying, first of all, I don't even understand the question, and two, I don't understand his explanation, what does that mean? That means you are not up to the current class standards. That means whoever you are, you got a lot of studying to do to understand this, right? And that's the beauty of me recording the class, because now what happens? If Jimmy did not know what the hell just happened, then Jimmy could put a note in his note and say, go home, study these, and then go back and watch the segment of video where Abel asked that question and Mr. Kim explained it, and see if you could actually appreciate and understand the explanation. That, boys and girls, is a mark of an honors student who's ready to do well in college, right? So if you just kind of dismissed what Abel said and you're just like, and you went across, right, then that makes you, I'm not saying in a bad way, an average high school student, right? If you want to be the excelling student, that's what you want to do, okay? All right, cool. Any questions, comments, concerns? Go ahead, sir.
So on the very bottom.
Yes, sir.
Reaction.
Mm-hmm.
Like I understand it doesn't work, but
Mm-hmm.
what happened to the hydrogen? Because you have NH3 on the reactant side.
Oh, I'm sorry, I screwed up. Hey, look at that. Thank you for calling me out. So look at this, right? So Mr. Kim messed up, right? Anyone know how to fix this equation? Back to you again, sir.
Would it be H4?
No, nope, because H4 doesn't exist, right? This what? I'm trying to write this as an acid, right, Justin?
Oh, so
Which means that it has to give a proton. So this took a proton, right?
Yes.
So this is pre-taking a proton. So that makes this what?
H2O.
There you go. Right? Awesome. Right? And you know what's even cooler? That's another, I'm not, guys, I'm going to say it. It's, right? Don't laugh. This is yet another mark of a student who's interested in class, because what happens? If you can fix your own question that you came up with, right? That's a really good thing to do, right? God, I thought I was going to go a week without complimenting Justin in the middle of class. All right. All right. You guys okay? There goes my Friday. All right, let's go. All right, good. Good point, though. Good pitch. All right, here we go. So what? To identify Arrhenius acid or base, it's easy. What are we looking for? We're literally looking for something on the molecule itself, right? So identify a presence of H at the front. Remember, the H needs to come off the front. Why? Because when it comes off, it doesn't just come off as H. It comes off as what? H plus, which makes that a what kind of ion? Cation. And according to IU Peck, you remember a long time ago when we did chemical formulas, usually positive cations are written when? First or second? First. That's why you want to look for H's in the front. Now, that's not always true, remember, but that's 99.65% correct. So, to identify something as an Arrhenius acid, you want to look for it in the front, okay? Bases, you want to look for OH. Now, why do we look for OH in the rear? Because how does the OH fall off? It falls off as a what? Just OH? Guys, we wrote the equation. How does OH come off? OH comes off as a what? OH minus. And according to IU Peck, where do we write anions? Towards the end, right? Right? And if you don't know that, think about it. Hey, isn't that how oxidation state, oxidation states work also when you were filling it out, right? Usually the ones in the back, like oxygen, are negative, right? And the ones in the front are positive, right? So that's why we're going to look for it like that. Okay. Everybody, okay? So that's what we're looking at, right? Now, that brings up another thing that's kind of similar to Abel's question, which is another species that looks like it could be polyprotic. I'm going to get to that in a second. To identify bronze and Lowry bases, though, then it's easy, right? First of all, acid, is it any different than Arrhenius? Nope, exactly same as Arrhenius. Exactly same as Arrhenius. So if you want to identify something as a bronzed acid, the methodology is exactly the same. The base is where it changes, though, right? It's a little bit complicated. In order to figure out if it's a bronzed base, then you have to actually take the thing you have, tack on an H plus, and then ask yourself, is this something that looks like it exists in nature? All right. So for example, excuse you, all right, for example, right, OH minus, right? Here's a advanced question, right? Ready? Now only raise your hand if you like getting stuff wrong and you don't care, okay? OH minus, would this be an Arrhenius base or a bronzed base? This is if I were teaching honors chem, this is what I would ask, right? All right, only raise your hand if you're not going to be embarrassed if you get this wrong, all right? Let's go. Let's go. Jacob.
Like a bronze base.
What do you guys think? Well, that's no fun. Jacob got it right. Why? Because you're thinking, wait a minute, Mr. Kim, I see an OH, right? Right? However, oh, could I get good morning, Misty? So not.
Take out the two.
Yeah. Let's go again. Okay. Could I get good morning, Misty? Evan Matt, not here. He's hiding.
Well, thank you. Have a great day and a nice weekend.
Could I have a nice weekend, Misty?
Nice weekend.
Yeah. All right. So going back to what Jacob said, right? It looks like it could be Arrhenius. Many of you might have said Arrhenius because you see the OH, right? Except, right? What is different? Jacob thought about the definition. Bronzed definition of a base is a what? Anyone other than Jacob? Yes, Sebastian. Right. Proton acceptor. And then you realize, wait a minute. This can accept a proton and turn into a what? Right. And remember what I said? To identify if it's a bronzed base, you ask yourself, if I stick an H plus on it, does it turn into something that I've seen before? Hey, how many people have seen H2O? So does that make, first of all, H plus acceptor? Yes. And two, because it's an acceptor, it is a bronzed base, right? Would Regents ever ask that? Nope. That's what you'd be asked probably in honors. I bet you if I walk down to honors room right now and ask this question, half the kids will get it wrong. But I don't. Why? Because when I do things like that, then none of them sign up for AP Chem. Right? Right. All right, moving on. All right. In fact, this is one of those, if you're taking general chemistry in college and then, not at like an Ivy level, but like if you go to like half decent schools, like, some of the schools up here that are not Ivies, and if you took general chemistry there, and then if you got this question, I bet you good half to 2/3 of like 300 plus students will probably be confused, right? And if you could explain this, right, they'll be like, oh yeah, you're pretty smart, okay? All right, here we go. So that's another example, right? Ammonia is a base. Why? Because ammonia can exist, right? So if you come across ammonia and then they ask, right, what is this? You'll say, oh, it's a bronzed base. How do we know? We know it because NH3, what do? You stick an H plus on it. And when you stick an H plus on NH3, what do you end up getting? NH4 plus, and then you ask yourself, does this exist? And the answer is table E says yes. Therefore, this is a legitimate equation, one. And two, in this equation, ammonia is taking a proton. So therefore, it's a Bronsted base, right? Not that you'll be asked this, but can you imagine if that was an FRQ question, right? Or how about this? Tonight, right? You want to go see the new Marvel movie, right? Because you've been busy, right? Because thing. So your parents are giving you a hard time because I want to go hang out with my friends, right? Hey mom, can I go see the new Marvel movie with friends after dinner? And mom says, well, first of all, Justin, we know you have no friends. That makes no sense. And two, no, it's Friday, right? But right, why don't you study some? And what do you say? Oh, okay. He goes, by the way, mom, ammonia, is that a Bronsted base and why? Right? And she goes, what? What do? Bring out the whiteboard and say, okay, everyone, take out your reference tables. Let's go. And you explain. Well, we know Bronsted base is what? A proton acceptor. And you can't just accept a proton. You have to be a legitimate molecule after you take a proton. Right? And say, well, NH3, could it take a proton? Well, let's try. If you take it, put it on, what happens? Get NH4 plus. Does that exist? Look at mom. And she goes, oh, I don't know. What do you mean you don't know? Did you not study table E, mom? And mom goes, oh, why don't you? And then she goes, oh, I did. Well, then don't sit there. Go there. Don't talk to your mom like that, though. And then what happens? She goes there. Goes, do you see NH4 plus? She goes, oh, why? Yes, there is. Goes, oh, so we know it's a Bronsted base. Oh, what do you know? Now can I go see the movie? How do you say no to that, right? All right. Whoa, that's another one. What? What do you think? Is NO3 minus, well, first we got to ask, is NO3 minus a thing? Remember, it has to be a thing on both sides. NO3 minus, is that a thing? And how do you know? Raise your hand. Yes. You got to speak up, man. Nitrate, table E. Boom, right? So we know that here it's nitrate, table E. So it's a thing. What about HNO3? Isn't that what happens when you stick an H plus on it? What would that be? Is that a thing? And do we know? Raise your hand. Yo, man, it's got an H in the front. Where do we go? What are you suspecting? If it's got an H in the front, what are you suspecting? It's a what? Is there a table for acid? Yes. What table is that? K for Kim, right? So is this a thing? Yeah. Table K. It's a thing. So therefore, right? What does it tell you? Left side, does this exist? Yes, it does. Does right side, does that exist? Yes, it does. And what do we know? The left side, did it take a proton or give a proton? It did this take a proton or give a proton? What did this do to turn into that? What? It took one, right? So therefore, what is this? If it takes a proton, what is it? Right, I know. What is it? Base, right? Everybody okay? All right. What up?
Are we going to be expected to identify bases that won't get reference?
No, that's a good question.
I know they have to list between.
Yeah, I would say there's a 92.6% chance you will not be asked to. You'll only be asked to. So actually, maybe I said this in the other class yesterday. An example of a Bronsted base in the regions, they're really stuck to using ammonia, right? They could say, they could do this. According to an alternate theory of acid and bases, which of the following would be a base, right? And then they list entire table L, right? Do you see that? That would be an interesting question. Do I have table L here somewhere? I'm going to go back. Table L, table L, table L. Oh, maybe I didn't get to table L yet. Oh, no, it's here. Come on. Come on. Ah, here we go. So, we got to go to the next one. Wow, that took a while. So imagine, right? They could do something like this and a multiple choice question. Which of the following is considered a base according to Bronsted-Lowry or alternate theory, right? Or they'll say, all right, according to some theory of acid and base, which one of the following would be considered a base? It's such a vague question, isn't it? However, you realize, wait a minute, and then you see what's going to happen. Kids going to raise their hand like, there's got to be a mistake, Mr. Kim. Choice, right? Because they're going to say, Mr. Kim, according to table L, that's a base, that's a base, that's a base, that's a base, right? So then you're like, so they're all the correct answers. No, because the question said, according to an alternate or a different theory of acid and bases, they may use Bronsted, the actual name. Which of the following is which one of the following would be considered a base then? Then you ask yourself, well, guess what? This is the only one that has a what? Different definition of a base, right? Everybody see that? Because this one is what? Hydroxide ion donors, and this one isn't donating hydroxide. It's base because it's accepting hydroxide, right? And then the question is, hey, Mr. Kim, how are these guys Bronsted base? It's easy. NaOH. Remember, Na, right? OH. Is that ionic, polar covalent, or non-polar covalent? Hello? What? Ionic. Hello, you should all know that, right? If you don't, you're writing OMG, OMG, right? Why is NaOH ionic, right? And you're studying that, right? Yeah, you want to explain why? Right, it has a metal and a what? OH is what? What? Right, polyatomic anion, right? But what else do we know? That's and then we go about that in water. What about in water? Solubility, right? NaOH would be what? Yes, sir.
Soluble.
Why?
Because
Right, Na is group what? And we say group 1 is what? Always soluble, right? All day, every day, right? Do you see that? That's why I like these last 2 units. I keep saying last 2, even though there's 2 more units after this, because this is a unit where literally everything's coming together. And you know what? As jokingly I said about Justin at dinner table, this is what makes you sound really smart in chemistry. Because if you actually can explain acid and base or redox by pulling things from other units, right? Kids are gonna be like, wow, you're a smart cookie, right? All right, so moving on. So let's go. So NaOH, right? Justin said it's fully soluble, right? Abel said NaOH is ionic because why? It's got a polyatomic anion. And Justin said and then looking at that, Justin said it is fully soluble because Na is group 1, right? And rule for group 1 is fully soluble. So you know that every single NaOH that goes into water will turn into Na plus, and what's the other half? OH minus. So remember, we're still talking about, well, Mr. Kim, how is NaOH considered a base according to Bronsted? Ready? Watch this. Even though NaOH can't take a proton, when it goes in water, it'll turn into OH minus, right? Can OH minus take a proton? Yes, that's why it's still a Bronsted base. Okay? All right, so let's keep going. There's Bronsted, Lori. Lori's upset. All right, so what? We did all of that. All right, let's keep going. Here we go. Conjugate acid and bases. What in the world is that? Somebody would have noticed something in the previous example, right? Conjugates, right? Here we go. What acid giveth, acid can taketh away. They can change their mind. Think about it. Sarah is an acid. And Raya is a base. Can't you tell? She's bitter. So nobody got that? Don't quote me out of context. Then you're going to be like, wait, did you just call a student bitter? Right? You get it, right? In a real funny class, if Raya had some sense of humor, she would slip away, right? No, you don't get that either. Slippery base. No. All right, moving on. All right, so look at it this way. If Sarah is an acid, according to Bronsted, what is she going to like to donate? A what? Sarah, what would you like to donate if you're a Bronsted acid? Right. different from hydrogen, right? H plus ion or proton, right? And Raya would what? If she's a Bronsted base, what would she be? Hello? Yeah. Right. So therefore, if you put the two together, right, Sarah's going to give off a proton, right? H plus, and then Raya's going to grab it because she's a base. Kids, can Sarah change her mind? Can Sarah change her mind? Of course she can. Of course you can. Sarah, you're going to be like, you know what? I actually like my proton back, please. So she's going to take it back. If she takes it back, what is she now? Is she proton donor anymore? What is she? She's a what? Receiver. Then what does that make her? A base. So what the heck is she? Sarah, what are you? You just donated a proton and you took it back. What are you? Acid or base? We don't know. And that's what this is about. Ready? So watch this. I'm going to close the door for a second. Wow. Every acid that donates, right? Think about it this way. Imagine acid is walking around with protons in their pockets. You got me? So if an acid donates a proton, yes or no, would it have an empty pocket? Yes. Theoretically speaking, then, could that acid now pick up a proton and put it in its empty pocket? So that means every acid, once it donates a proton, has now become eligible to be what? A base. That's a novel concept. So every acid, once donates a proton, is now eligible to be considered a base. Everybody okay? So remember, acids donate protons, but what's left after acid donates it? Well, look at HCl. HCl can donate a proton, right? But if HCl donates a proton, then what happens? Proton is donated. What's left of HCl after it gives up an H plus? Look at it and think. If HCl gives up an H plus, then what are we left with? Can I get some new people other than the same few people keep raising their hands? Right? Jacob. Chlorine, just Cl. Cl what? -1. Right? That's a few people talk about diatomic, right? Don't do that. If you thought diatomic, you got to write a note on the side, right? Don't screw up diatomic again, right? All right. Cl minus. So what's left after acid donates its proton? You're left with a what kind of ion? What kind of ion are you left with after acid donates its proton? What is that? It's a what kind of ion? What kind of ion? What? Anion. So when an acid donates a proton, it's left with a more negatively charged ion, right? And in theory, couldn't Cl minus grab a proton and turn back to HCl, right? Does Cl minus exist in nature? Yes. Does HCl exist in nature? Yes. So therefore, could it grab a proton? Yes. So Cl minus, right, is now a base. What's up?
When an acid turns to a base, then takes it back a proton, does it count as a reverse reaction, or is it just two separate reactions?
That is a reverse reaction, but that's not what we're going to focus on right now. The question is, we still have to figure out what the hell is Sarah? Is she an acid or base? Right? Right? Because she can be an acid and donate a proton, but then all of a sudden she'll turn around to rise. Like, changing my mind, take it back, right? Now she's a base. So what is she? Is she an acid or base? Question is, right? Sarah is HCl. What kind of acid is HCl? Raise your hand right there. Is there something you wanna be drinking? Yeah. No. What is it? What is HCl? Yeah, that's your stomach acid, boys and girls. Hydrochloric is your stomach acid. What's the problem with your stomach acid? What happens if you swallow a whole chicken bone? like right now, what would happen by tomorrow this time? That bone is gone. Why? The acid completely dissolves it. How do I know? Because my 8th grade science teacher did that. He had a kid bring in a chicken bone, and a kid brought in a drumstick. Right? He didn't realize he needed the bone, so he brought in a drumstick, right, from roast chicken, right, or whatever. And the teacher made the kid eat it in class, right? But back in those days, you can do that. Like he goes, Mr. Marin, he goes, go now. And then he timed it, and the kid's like eating as fast as he can, right? Nowadays, I can't do that because if I do that, and God forbid, Sierra chokes on it and then she falls down, right? I'm going to jail or getting deported, right? So anyway, so the point is, he did do that, and then he took the bone, stuck it into a glass beaker, and then he took 12 molar HCl, poured it in. 12 molar HCl is the same concentration of the HCl found in your stomach. And then he covered it with aluminum foil, put it to the side. Super dangerous because, God, you know what happened if a kid decided to, stick their finger in it, right? He left it. Next morning, the same class, he took a pair of tongs, reached in, grabbed the bone. The bone was still there, right? We're like, hey, nothing happened. He grabbed the bone. When he lifted it up, the whole bone was like loose. It looked like jello. And when he lifted it, it just broke into pieces. And when it hit the desk, it just, broke. It just right into goo. We're like, whoa. And then, oh God, holy hell, the smell, right? From that bone. It was digested food. What do you think it smells like? Yeah. You know what a digested food smells like, right? Yeah, it comes out the other end, right? So anyway, that's what it smelled like. Kids are like, yeah, right? But it was so shocking and graphic that we all remember. So that's your stomach acid, HCl, strong acid, right? The only reason why we're not. So think about it. Once you stop producing acid, once you stop, so why doesn't our stomach get eaten? Yeah. Yeah. What is that lining? Anyone? It's not acid-proof lining. Yeah. Mucus. All the snot that you have in your nose, that is created all the way down your path, down into your stomach. And not only that, your stomach has the most amount of mucus anywhere, and mucosal cells, and they're called goblet cells, and they keep producing mucus. All right. So what happens? It's kind of like when the acid is coming out, it's digesting everything in your stomach, but it's gonna also try to digest your stomach, except it can't get to it. Why? Because your stomach keeps producing so much mucus that the mucus is getting eaten away by the acid, so acid will never get to the actual cell. What happens though if you don't produce enough mucus? You get damage. That's called ulcers, right? Ulcers, right? And fun fact, back a long time ago, they didn't realize what the solution to ulcers. They just said, oh, stress causes ulcers, right? But it turned out majority of the ulcers actually caused by bacteria, right? Right? It's caused by bacteria. Why? Some bacteria actually dissolve, they eat mucus. So can you imagine though, if you had this group of bacteria infect the inside of your stomach, it'll start eating away at the mucus, which means your mucosal lining is thin. Then what happens? Your acid will actually eat through the mucus faster and you'll get ulcers, right? So crazy thing, back in the late 80s, some doctor came up with the idea that what if we treat them with antibiotics? And people are like, what the hell are you talking about, right? And what happened to these people? They got cured of their ulcers, right? And people are like, oh, I thought it was stress-induced, right? So understanding bio and chem is really interesting, even in a doctor level, right? It allows you to do some amazing stuff. All right, so let's go. HCl. So now what do we know? HCl is a strong acid. What is Sarah? Just look at her. Is she a strong acid or a weak acid? She looks pretty strong to me. Really? Right. So she's a strong acid. Acids like to what? Donate a what? Protons. If she's a super strong acid, how willing is she to donate those protons? Very much. Very, very much. So, Sarah, if you want to donate your protons so much, what does it tell us about your likeness of protons? Do you like them or do you not like them? You want to donate them all the time. She hates protons. Strong acids hate protons. Strong acids hate protons. Sarah is a strong acid. Why? She hates protons. That's not what's gonna happen. As soon as she sees somebody can take it, what are you gonna do? You're gonna take it. Ew, ew, take it. I don't want this proton. Okay? Everyone understand that? Now she's Cl minus. What can she do with proton? Give another one or take one back? Take one back. Remember, this is the part where we're confused because what are you, Sarah? Are you a base, right? She could take it back, but what do we just say? Cl minus, HCl is a what kind of acid? Strong acid. How much does she like the proton? She hates it. Strong acids hate proton. That's why she got rid of it. If that's the case, are you gonna want to take one back? No. You could if you want to, but would she want to take it back? Hell no. Rye's like, you know what? I'm sorry, I changed my mind. Can you take this back? I was like, no, but you're now a base. You can take it back. She's like, yeah, but I hate protons. So that is how strong acids work. Strong acids hate protons, so therefore what happens? They like to give it away and stay giving it away. So even though they could take it back, they don't. So now, ready? Think about this. If she could take it back, she's a base, right? But does she want to take it back? No. What kind of base is she then? Really good at it or really bad at it? Really bad at it. So there you go. When a strong acid gives up a proton, it becomes a base, right? But what kind of base? Strong or weak base? Yeah, super weak base. We literally explain what a conjugate acid and base is, okay? And that's what it's called. Conjugate. When you conjure in magic, what are you doing? You take your wand, and you conjure up a what? If you had the power, what would you conjure up right now? Right now. Really? I would have been like world peace.
Oh, no.
Make right? World peace and turn all negative politicians into just pure energy. And then put them back in the center of the universe, right? No. Mr. Ken, that's like Thanos. I know. I get so upset when I watch like Marvels and Thanos goes and then like random people. Like, why would you do that? Why would you do this and say all the evil people had evil thoughts, right? Who wanted to do evil things, steal things, hurt people, right? Turn them back into energy, right? Like, yeah, but what happens if you do this and then you disappear? Well, oh well, right? Anyway, so moving on. So, you understand that? Strong acids don't like their protons. That's why they give it away. That's why they're strong. Did you write that? Strong acids don't like protons. That's why they give it away, right? Strong acids don't like protons. That's why they give it away. That's why they are a strong acid. Once they give it away, they are a base, right? Remember? But what kind of base? Weak base, because they don't want to take it back, right? Everybody okay? And that, what is that called? That's called a conjugate base. Because when you conjure, you're making it up out of thin air. So when an acid donates its proton, she's now a conjugated base or conjugate base, right? And what happens? Conjugate bases are the opposite strengths of the acid it came from. Everybody okay with that? Conjugates are opposite strength of what it came from. So strong acids form what kind of base? Weak conjugate base. What about a weak acid? What do you think? What kind of conjugate base do you think that will form? Yeah, strong conjugate base, right? It makes sense though. Think about it. If Eden is a weak acid, that means you want to donate proton, but how committed are you at donating a proton? Is she good at donating protons if she's a weak acid? Right. Weak acid means what? You're good or bad at your job? Bad at your job. What is the job of an acid, according to Bronsted? To what with protons? Give it away. And if she's a weak acid, are you good at giving away protons? No. Because why? She's still attached to them. Remember Sarah, the strong acid? She's like, ew, protons, they gross me out. I don't want it, right? What are Eden? He's like, you know, I could give it away, but I don't know. They're all so cute. Which means what? If she does give it away, she was somewhat attached to it, right? So if she doesn't give it away, what is the likelihood to want to take it back? Really high, right? If you're really, really, really willing to take a proton back or accept it, what does that make you according to Bronsted? Don't worry about getting it wrong. Come on. What do you think? There you go. Right? So weak, that's what Kiernan said. Weak acids will form strong conjugate base. Strong acids will form weak conjugate acid. Right? And that's the explanation. Okay? All right. Let's keep going, guys. So here we go, right? Look at this, right? What is that? What is that? Strong or weak acid? Right. That is a strong acid. Did you write that it loves or hates protons? Hates protons. This is the what? What is this? What is this? Conjugate base, but how much does Cl want it back to go back to HCl? Therefore, it's weak. But if you think about it, right, this makes perfect sense. Why? Look at the solubility rules. What's Cl minus? Halide. What's the rule for halide? Solubility. Oh man, you have to look that up. What? What? Chlorine, sodium chloride, potassium chloride, right? All chlorides or halides are what? Soluble, except for lead, mercury, and silver. You should memorize that, man. I know for Regents you don't have to, but it'll make you a better student if you memorize it, right? So all halides are fully soluble, right? According to table F, right? HCl. How soluble is HCl? Then. How soluble is HCl then? Cl minus. What's the solubility rule? Soluble or not soluble? Soluble. Soluble is what? It stays as ions in water, right? That's why HCl is a strong acid. Because Cl minus likes being Cl minus, not HCl, not NaCl, not MgCl. That's why they're highly soluble, right? So therefore, how good is Cl minus in picking something up and turning back to molecule? It's bad at it because it's happiest as an anion in water, right? That's table F telling us that, okay? All right, let's keep going. After the HCl donates, it becomes Cl minus. What can Cl minus do? Can it donate? So this is a rehash, right? So if you wrote down everything I said, you're good to go, right? So what can Cl minus do? Can it donate another H plus? Yes or no? Can it donate another one? No, no. Why not? Why can't it donate another proton after it donates us H? What? It's an obvious answer. What? Doesn't have another one. Doesn't have one. Have another H plus. Duh. Right? Let's keep going. So it can accept, yes? And turn back to the OG acid. Right? But what do we know of the OG acid? It's a strong acid, which means what? Wants to donate. Why the heck would it take it up if it wants to donate it, right? So therefore, it's really bad at taking it back, making it a weak base, okay? So what is it called if it accepts? It's called a what? If it accepts a proton, what is it called? It's a what? Proton acceptor. Base. But what kind of base is it? Was it born there or was it created? Created. Out of what? Of the acid. So that makes this a conjugate base, right? Everybody okay? Well, conjugate Bronsted base. Big deal, right? After it donates H plus, it becomes Cl minus. This is able to act like a base, so we call this a conjugate base of HCl. So this is the key knowledge, right? Oh, sorry. But what else we know? But it's a poor base. Therefore, Cl minus is a weak conjugate base. Everybody good? Oh, all right. Not gonna lie, man. This is heavy. It's a lot of material. I'm not gonna lie, it's a lot of material. So therefore, you probably want to review this stuff, right? Not to mention, let's be honest, right? Most of you in here, there are parts of this class when we're conversing, you're like, oh yeah, I forgot about that, right? So don't forget about that. All right, let's keep going. All right, we know this, right? Right? After donating H plus, acids become a what? Conjugate base, not base, and acid. And then it's not always weak or strong, right? It's based on the strength of the original acid or base, right? So they don't all turn into weak conjugate base, right? It depends on who you start with. You can write that down, right? Strength is based on the original thing's strength, right? Yes, sir.
If you have like a strong acid that gives a proton, if it takes it back, could it take it back like spontaneously, or would it?
It would, but as soon as it takes it back, what is it going to do?
Give it up again.
Yeah, it's gonna, as soon as opportunity rises, it's gonna pop it off again, right? It's kind of like that annoying kid. It's like, Tommy, hold on to your hat, right? And Tommy keeps taking it off, right? How much do you want to slap Tommy at this point, right? Dang it, keep that hat on. Tommy keeps putting it off, right? Why? Tommy hates hats, right? So if hat was a proton, he'd be really good at acid. So what do you say to Tommy? Tommy, you're not an acid, and that's not a proton. And if Tommy goes, what you talking about, right? So what do you do with this 3-year-old? Explain to him acids and bases, right? And then what happens? He'll cry. Because why? You're boring him. Except what's going to happen? He's never going to take his hat off again, right? Like, you want another lesson in Bronson acid and base theory, buddy? Right? Everybody good? Right? You tape him down to a chair, put toothpicks in his eyes to keep his eyelids open, and explain it to him. Of course, when the parents are not there, right? Right? And then when babies and the parents come back, like, wow, Justin and Tiernan, you guys are such good babysitters, right? Whenever you say, Bronsted, Tommy behaves, right? All right, so I'm kidding. Don't do that. All right, here we go. So here we go. So NH3. Guys, look at this equation. What is NH3? Raise your hand once you figure it out. What is NH3? What is NH3? What is NH3? Somebody knew. Yes. A what? It's an ammonia, yes. But what about ammonia? What is it? What is it? What is it? What is it? Dude, I see the same 4 hands, man. It's getting boring, right? Plus, I already complimented Justin without wanting to. Don't make me do it again. Come on, man. Let's go. Yes. It's an acid or a base. Look at the picture, Rafaela. Is NH3 taking a proton or giving a proton? NH3 turned into a what? And yeah, so in order for it to do that, did it have to take an H or give an H? NH3 turned into a 4. Yeah, but you said give. Yes. I'm confused. Did you? Guys, this is why you speak out, because I can't hear you, all right? So yes, it is an acid. No, it's not an acid. It's a base. Wait, no. Hello. NH3.
Yes.
Is it taking a proton?
Yes.
Is it taking or giving a proton? Taking a proton. Pause. Pause. Okay, now ask yourself. According to Bronsted, taking a proton is an acid or a base? There you go. So NH3 is a what? It's a base. Everybody okay? So it's a base, right? Now, if you're confused, you could also say Bronsted, right? And then you can put a star. Why? That's what you go review. Like if you're sure, it's just gonna be like, all right? Let's face it, right? You're not the only one. There are people that are confused around it. I know so. Why? Because guys, this is not an easy topic. But Mr. Kim, I understand. Like, you remember I told you, if you find this easy and you feel like you're so smart, who's the actual smart person? It's me. I'm so smart. I'm explaining so well. You want to be smart? Be able to do this tonight. Then you're also smart. All right, here we go. So, right, thank you, Rafaela, for being honest with this. All right, so it's a base. But once it accepts a proton, it turns into a what? It turns into this, right? Now, back to Rafaela. NH4 plus, could it take another proton or could it give a proton? It could give a proton. If it gives a proton, pause. What is it, acid or base? Acid. Now it's an acid, right? You okay? All right, so that turns it into NH4 plus, and she knows this is an acid. Everybody okay with that? So what is the take-home lesson that Rafael is giving us? Everybody, you rush this, you're going to make a mistake. I guarantee you. If I rush this, I'm going to make a mistake. In fact, didn't it happen earlier? Right? So do not rush it. You got to pause. You got to ask yourself. Again, being able to regurgitate that table of Lewis and Arrhenius acid and bases on your test or quiz or regions is a plus. Being able to do that. This is why please try not to copy this into a reference table. I've had kids do that. They write the table into the reference table because, I let you use it. But what happens when you do that? Come real regions, you're not going to be able to do it because right, it was written there, right? So try to not do that. Why is the board flickering and blinking, right? All right, so moving on. NH4 plus is about to lose that extra H plus, turning back to NH3. So therefore, losing makes it a Bronsted acid, right? How many people think that you understand what's going on in class right now? Let's be honest. Yeah, there you go. How many people think that this is a little bit confused? It could be a little bit confusing. How many people think that if you don't review this, you're definitely going to be confused the heck out of this by Monday? Exactly, right? Right? So make sure you do that. I'm telling you right now, you walking out of this room, I've armed your heads better than honors chem. I guarantee you. However, the difference with honors and regular class is this. I'm not going to say all because some of those honors kids are really lazy. Honors kids, if they don't get it, what are they going to do? They're going to go home. They're going to start studying. They're going to read. They're going to get stuff done, or their parents are going to get them tutored, right? Either way, they're going to do that. They're going to do the work, right? So this is like the tortoise and the hare, right? You got a head start because you're such an amazing, good-looking teacher, right? Well, work on the momentum. You're on a high momentum in terms of understanding this, right? Right? So make sure you run with it, right? Yes, sir. I thought you were going to say you're not taking it. What?
Is there any correlation between acids and bases and product or reactant side?
Absolutely. Absolutely.
Like, since usually on.
No.
Oh, because they're giving.
Weak acids and strong acids, right, being the strength, will determine who is usually the acid or base. But that has nothing to do with regions. They're not even going to go ask you that, but that's a really good next question to have, right? For that, we go into another whole topic called equilibrium and rate laws, which is what honors supposed to do, and they memorize it. And then when they do the equilibrium rate law, they memorize what happens in those cases. And then when they came to AP Chem, they're like, you remember that? Why does it do that? And they're like, I don't know. And it's like, we're going to calculate it using math and some calculus, right? That's the hierarchy. All right, let's keep going. These are great questions. Lewis has some basis. Not on the regions. That's all I wrote. Not on the regions, right? But you remember what I did say, right? If you are interested, it's an electron acceptor and donor. And what happens? They flip-flop. They go backwards. So Bronsted was an H plus donor. Now it's an electron acceptor. But guys, it makes perfect sense, because if you think about it, right? Right? Look at that, right? Look at this. That is a Bronsted acid or Arrhenius acid. Do you agree? What's the charge of HCl right now? What's the charge? What is it? Neutral. But after it gave the H plus, what is the charge now? Negative, right? So Lewis's definition says that if HCl picks up a negative, it's going to have to give off the hydrogen. That's what Lewis is saying. All right. So Lewis' definition is essentially, right, acid is an electron acceptor, base is an electron donor, right? And why is that important, right? Why is that important? Because of what DNA is. DNA. Anyone know the formula for DNA? It's really complex, right? You remember phosphate backbone, and it's got nitrogenous bases and all that stuff, right? But according to Lewis, it's a deoxyribose nucleic acid, right? And according to Bronsted or Lewis, what happens to acid when it goes into water? It gives up a what? Proton. And then it itself becomes what charge? HCl turns to Cl, right? Negative. So what happens to DNA when it goes into water? There's negative. Right? Isn't that wild? That's why we put the name acid. And you'd be surprised if I ask grown-ass college kids, why is deoxyribose nucleic acid acid? They can't explain it. Some kid will be like, oh, because it gives off protons. Yes, it's true. Then I ask them, hey, dumbass, which proton? And they're like, oh, I don't know, it's so complex. The easiest answer is this. Lewis' definition of acid says an acid is an electron acceptor. DNA becomes negatively charged. How do we know? If you put a electrolytic cell, guess where DNA goes to? It goes to the positive side. You'll see it moving towards the positive side. That's how we know DNA is negatively charged in water. Right? And if we knew that third definition of acid bases, we're like, oh, wait a minute, it's an acid. That's why the people who figured out DNA, right? Well, they said, oh, it's a deoxyribose. Deoxyribose is the chemical formula that makes up the backbone, right? Nucleic, ATGC, nucleotides. So it's a backbone is deoxyribose. Nucleic is the center, ATGC, but it's a deoxyribose nucleic that makes a what? An acid. It's negative in water, right? And then they realized, wait a minute, DNA goes to positive because it's negative, right? And then all of a sudden, some guy came up with the idea, what if we make it a race? Give it a puzzle, a maze to go through. Wouldn't the fat, chunky DNA have slower time going through, and then small little piece of DNA go through faster? They're like, yeah, wait a minute, why don't we do that? Why don't we take a gel with microscopic pathways, random pathways, put DNA on one side, put positive on the other side, and put a crap ton of electrical current. What happens? DNA will start moving through. And what happens? Slower guys move faster, fat guys, longer guys move slower. And what happens? They start making a pattern. What did we just discover? DNA fingerprinting. Isn't that wild? That's chemistry and biology put together. And some guy decided, right? That wait a minute, we can actually do that. And if we do that to Justin's DNA, because all the sizes are the same, they'll always look the same pattern. And then we just realized, oh my God, we just figured out how to do a fingerprint of DNA. It's all based on this, right? How cool is that? Right? The second story of dumping my girlfriend was this. Same girl. I'm sitting in advanced bio class, and her friend, who's also an honor scholar, comes in 1 year older than us, right? But she skipped a year. So she graduated in 3 years. I graduated in 5 years. Because, I did a second major, but she skipped. So she graduated in 3 years. I went to med school, right? Anyway, so they're saying that she's friends with all the upperclassmen. They come in and she goes, oh my God, I just came in. I ran my DNA backwards. Because when you run the gel, you guys know what I'm talking about now, right? In living environment, the gel DNA electrophoresis, there's a plus and minus, red and black wire. And then what happens? They plug in opposite end, right? So she goes, oh, I plugged it in the wrong end. And my ex, she goes, oh, so funny, I've done that too. And I look across, I'm like, what the hell, you guys, what? They're ranked number 1, right? My grade and upper grade, right? And I look at them, what's the next thing that came out of my mouth? I said, but it's deoxyribose nucleic acid. It's a Lewis acid, right? Electron pair acceptor. It's negative. Of course it goes to which thode? Anode or cathode? If it's negative, cathode. So the first thing I said is, of course it goes to cathode, which means the side you want the DNA to go to, that wire, what do you plug it into, the plus or the minus? Plus, how do you get how do you get that wrong? Right? And they both looked at each other and they're like, what the hell's this problem? My problem is, how do you not put chemistry and biology together? And how are you honor students? Right? You're thinking, my God, Mr. Kim, right? No wonder you dumped this girl, right? Wouldn't you? Right? Anyway, no, that I'm not making it up. I'm sitting in what class was that? Special topics in human genetics, right? And it's dark, and I'm sitting there with my ex-girlfriend, right? We're taking well, she wasn't my ex-girlfriend. And then this other girl, Linda something, she comes in and late because she just came from lab. She's like, she sneaks in the dark. She's down and she goes, and she's like shaking her head. My ex, she goes, what happened? She goes, she turns around, taps her on the shoulder, goes, I ran my DNA backwards. And then she goes, oh, and they're like, yeah, I've done that too. And I was like, what? First of all, I was like shocked that the girl said it. And the second time she goes, I did that too. I was like, what? How could you screw that up, right? So now what's going to happen? Justin's going to be in college. He's not even going to care about science. And all of a sudden, somebody in a hallway, you're walking down the hallway, eating your, I don't know, gyro sandwich or something, right? Minding your own business. And you hear a bunch of like pre-med nerds saying, wait, which direction does DNA run in a gel? And you're going to stop, like, the record screech crack sound, and you turn around with your mouth full of gyro sandwich. I only say that because Rutgers had the best gyro sandwiches. You're going to be like, cathode. Turn around and walk away, right? How badass is that? Because they're going to be like, wait, why? And they're like, wait a minute, he's correct. Why? Hey, you, come back, right? You with the sandwich, right? Why is it cathode? He goes, deoxyribonucleic was nucleic acid. I don't remember who it was, but somebody said it's a proton donor, right? Becomes negative. Then what do? Mic drop. You don't have a mic, so what do? Drop the gyro sandwich and you walk away, right? Think about that, right? Anyway, moving on. Remember, both strong acids and strong bases dissociate 100%. We said this in the beginning, though, right? I think it was Abel who said something, and I said, hey, it completely dissociates, right? Strong acids and strong bases dissociate 100%, right? Oh, this is moving on to the next big, huge thing, right? Meaning, hello? What the heck is this? All right, ready? Let's go. Let's make this the last slide. Let's go out strong. HCl. What does it turn into? Can you finish these equations? Yes, we can. Right? Bob the Builder. Let's go. No, don't raise your hand. Do it. HCl is easy, right? I'm going to just show it to you, right? Oh, Mr. Kim, is that what you're talking about? Yeah, dude, if you had to see that and be like, oh, that's what you want me to do? You don't know how to do this, right? So know how to do dissociation equations, right? Can you do the next two? All right. Hey, next one's a little bit complicated because what kind of acid is it? It's a what? What? Good, thank you. Polyprotic. Guys, come on, man. Don't let Justin answer all the questions, right? Come on. It's polyprotic, right? What do we know? Polyprotic? More than one protons. But I don't see a proton. I don't see no proton, man. I only see an H+. Look, Ma, H+ is a proton, right? So did you write that? I hope you did. And then NaOH is easy, right? Hey, can you believe, right? 1 year on Regents, I saw this. They said, finish this equation. You know what kid wrote? Right? This is when I have to reconsider my life choices as being a teacher. That should be the equation, right? NaOH. And you're thinking, oh, Mr. Kim, how would the kid know? Of course the kid will know. Why? Because NaOH, when you see OH, what are you thinking? It's probably a what? No, NaOH. When you see the OH, what are you probably thinking? OH. It's a what? Acid or base? OH. Base. What kind of base? Whose base? According to who? Arrhenius base, right? Then what do? Double check by going to table. Base, L. Come on, man, get with it, right? base, right? And you double check that it's base. And then what do we know? Base is what? Dissolve or dissociate or decompose? Dissociate. That's why it dissociates, right? What is this? You're decomposing it into elements, right? Right? To which you said, what the hell are you doing, right? Everybody okay? And I think that's it. So we'll pause right there, all right? All right, good job, everyone. High fives all around.